Hello and welcome back to College Algebra. This is section 5.4, the second part, and two questions in section 5.5. Reminder before we get started that homework and quiz number 12 are due Friday, April the 17th at 11:59 p.m. Mastery quiz number 4, which is the review for test 4, is due Sunday, April the 19th at 11:59 p.m. And test 4 will be taken at 9 a.m. on Monday, April the 20th. All of the times in MyLabs Plus are Central Time. Please note that 9 a.m. on a Monday is our typical class time. Let's get started with the second portion of section 5.4. Section 5.4 discusses exponential and logarithmic equations. In the previous video, I talked about the exponential equations and how to solve those. In this video, we will be talking about solving logarithmic equations. There are two types of logarithmic equations that we will be solving. The first type, we will be solving using something called the equality property. If you can have two logarithms in an equation, one on the left side and one on the right side, they both have the same base. For example, log base b of u is equal to log base b of v. Then we can essentially drop the logarithms and say that u is equal to v. And then we can solve that equation. Let's see how that works. Notice that in the directions, not only does it tell us to use the equality property, but it also tells us to reject the values that are not in the domain of the original expression or expressions. As we look at this very first equation, we notice that there is a 2x plus 1 in this logarithmic expression. In order to check the domain, we will take what's inside here, this 2x plus 1, and we're going to set it greater than 0. We remember from a previous section that what we take the logarithm of must be positive. So we'll take 2x plus 1 and solve this inequality. Subtracting 1 from both sides, we get 2x is greater than negative 1. Dividing both sides by x, by 2, I get x is greater than negative 1/2. So we say that the domain is all values which are greater than negative 1/2. We'll come back and talk about this in just a moment. Let's go about solving the equation now. We start by saying that we have the log base 3 on both sides. So we take whatever is inside of that logarithm and we set those two expressions equal to each other. So we have 2x plus 1 that we will set equal to 11. This gives us a very nice linear equation, which we can solve by subtracting 1 from both sides. That gives us 2x is equal to 10, and then dividing both sides by 2, so we get x is equal to 5. Since 5 is in the domain of my expression, then 5 is the solution. So this is the solution for this equation. Moving on to problem number 2, the first thing I notice is that on the right-hand side I have two logarithms. On the left-hand side I have a number in front of my logarithm, even though I have the same logarithms on both sides. So the very first thing I need to do before I can do any kind of solving is I need to condense both sides using the logarithmic properties from section 5.3. So we condense the first side by taking the coefficient and making it an exponent. So the left-hand side becomes the natural log of x plus 5 raised to the second power. The right-hand side will use the product rule, which says that if I have the sum of two logarithms, I can multiply these two numbers. So on the right-hand side, 12 times 3 is 36, so we get the natural log of 36. Again, I want to talk about the domain, so we will take the expression x plus 5 and we will set it greater than 0 and solve for x. Subtracting 5 from both sides, I get x is greater than negative 5. So the domain is all values of x which are negative 5 to positive infinity or greater than negative 5. Let's go solve the equation and see what we get. We now have natural log on the left side and a natural log on the right side. So we can take the expression x plus 5 squared and set it equal to the value of 36. We should recognize this as a quadratic equation which we solved back in chapter 1. We solved these by taking the square root of both sides, which gives us the equation x plus 5 is equal to plus or minus the square root of 36, which is 6. Now I can take each of these equations, one being x plus 5 is equal to 6, and the second one being x plus 5 is equal to negative 6, and I can solve each of these for x. I subtract 5 from both sides, and I get x is equal to positive 1. On the second one, I subtract 5 from both sides, and I get x is equal to negative 11. Some of you may have recognized that negative 11 is not in the domain of my original expression. So for that reason, we're going to make a statement here. Since x is equal to negative 11 is not larger than negative 5, we reject x is equal to negative 11 as a solution. So it is not a solution. Therefore, x is equal to positive 1 is the only solution for this equation. And that's how we use the domain to check our solutions. Moving on to problem number 3, we see a similar thing that we encountered in problem number 2, in that on the left-hand side of this equation we have two logarithms. On the right-hand side only one. So before we can get started, we need to condense this left-hand side. So condense the left first. Okay, so using the product rule, we condense the left-hand side to now read log base 2 of x plus 3 times x minus 4 equals log base 2 of x plus 12. Notice we did not change the right-hand side. Let's go ahead and simplify this product inside our parentheses here before we go about doing anything else. This is going to become x squared minus x minus 12 on the left-hand side. Now, this is a little bit more complicated in terms of checking for our domain, but we can still do this. So let's come over here to the side and talk about the domain of these expressions. We've done something similar to this earlier in the semester, and we just have to check for the most restrictive one. So we're going to take x plus 3, set it greater than 0. We find that x must be greater than negative 3. Then we look at x minus 4, trying to do these in order. Set it greater than 0, and we discovered that x must be greater than 4. X is greater than 4 is more restrictive than negative 3. So now we move to x plus 12 is greater than 0, and we find that x must be greater than negative 12. When we say more restrictive, if I were to pick a number, let's say for example negative 10 is greater than negative 12, it is not greater than 4. So we need to pick the most restrictive, and this is our most restrictive domain. So we need to make sure that any value we select or find to be a solution is greater than positive 4. let's go back to solving our equation. Now that we have one logarithm on the left side and one logarithm on the right side, we can take those expressions inside our parentheses and set them equal to each other, and then we have an equation to solve. To solve this equation, it is quadratic. We're going to move everything to the left-hand side and set it equal to 0. X squared now, subtracting x from both sides, minus 2x. Subtracting 12 from both sides gives me minus 24, and this is equal to 0. X squared minus 2x minus 24 will factor, and it will factor into two parentheses. That is going to be x minus 6 and x plus 4. That product does give me negative 24 at the end and negative 2 in the middle. Remember, I still have to set each of these factors equal to 0 in order to find out what x might be. So for the first one, I add 6 to both sides. I get x is equal to 6. The second one, I subtract 4 from both sides. I get x is equal to negative 4. If I were to look at negative 4 is not greater than positive 4. So negative 4 must be rejected. So we reject this because it is not greater than 4. However, x is equal to 6 is greater than 4, so we can say that the only solution is x equals 6, and this is our solution. Very good. Number 4, we have lots of logarithms, but there's a logarithm in every single expression, which tells me I'm solving the same type of equation. So again, I must condense the left side and condense the right side. Now, I can look at these in terms of the domain before I do any condensing, and that might be helpful also. So we'll look at each of these pieces. X must be greater than 0. Then we look at 2x minus 3, and we solve that inequality. This tells us that 2x must be greater than 3, and x must be greater than 3 halves. 3 halves is larger than 0, so this so far is my most restrictive. 2x greater than 0 gives us the same thing as x is greater than 0. And then finally we have x minus 1 greater than 0, so x must be greater than 1. Still, my largest value is 3 halves, and so this is my most restrictive domain. Now let's condense so we can solve. So condensing each side, the first thing I'm going to do is to write this as x squared. I'll take an extra step in here so as not to lose you all. The second side over here, the right-hand side, we can write this because this is the difference of two pieces, two natural logarithms. We can go ahead and write this as the quotient. So I have 2x over x minus 1. On the left-hand side, now I'm going to take my difference of two natural logarithms, and I'm going to write this as the first part, x squared, divided by the second part, 2x minus 3. And we will have two natural logarithms which are equal to each other. Since they are both natural logarithms, we can simply look at what's inside those and set them equal to each other. So we will take x squared over 2x minus 3, and that will be equal to 2x over x minus 1. I'm going to solve this by cross multiplying. So I have x squared times x minus 1 is equal to 2x times 2x minus 3. Simplifying this, I get x to the third power minus x squared is equal to 4x squared minus 6x. It is a polynomial equation which we are going to solve by moving everything to the left-hand side. This will give us x cubed. Subtracting 4x squared from both sides gives us minus 5x squared. and adding 6x to both sides gives us plus 6x, and this is equal to 0. In order to solve this, it is not quadratic, but it does have a greatest common factor. So we can factor an x out. That's going to give me x on the outside, and then on the inside of the parentheses, I have x squared minus 5x plus 6, and this is equal to 0. Scrolling down the page just a little bit, this quadratic will factor also, and it factors into x minus 6 and x plus 1. That gives me, no, it does not, and that is probably the same thing you guys ran into. So what's going to happen here? We have to change our factors. What are some other factors of 6? Sometimes it's fun to do that just to make sure you guys are paying attention. So what are some other factors of 6? Let's try 2 and 3, because notice what has to happen here. I can't have a positive and a negative, and I think that's probably a mistake that so many people make. I need to look at this and say the signs have to be the same. This tells me they both have to be negative. So there we go. So now I have minus 2, minus 3. That does give me, now we get positive 6 and a negative 5 when we add them. Now we have 3 factors. X is equal to 0. Yeah, we're going to reject that one. X minus 2 is equal to 0, and x minus 3 is equal to 0. When we solve the second equation, we get x is equal to 2, and when we solve the third equation, we get x is equal to 3. So we have 1, 2, 3 equations, 0, 2, and 3. If we look back over here, we need to only use the ones which are greater than 3/2. So x is equal to 0 gets rejected because it is not greater than 3/2. So we only have 2 solutions, and those solutions are x is equal to 2 and x is equal to 3. So just 2 solutions for this equation. All right. The other type of logarithmic equation, and I tried to color code this for you guys, is what happens when we only have logarithms on one side of the equation. So when we have this happen, we can rewrite these logarithmic equations into their exponential form, and they become much easier to solve. Keep in mind, we talked about this in section 5.2, that y is equal to log base b of x can be rewritten in the exponential form of the base to the y power is equal to x. Now keep in mind, I'm going to go through here and I'm going to label these pieces for us. So this is y in this expression. B is the value here of 2. And our x expression is this entire piece in here of 4x minus 7. And so now let's rewrite this into its exponential form. Our exponential form says we take the base, so 2, to the power of the exponent or the value, so 2 to the third, is now equal to 4x minus 7. What a nice equation to solve. So 2 to the third is 8. So we have 8 is equal to 4x minus 7. To solve this equation, we add 7 to both sides. That gives me 15 is equal to 4x. And then we can divide both sides by 4. And so I get x is equal to 15/4. Most of the time it does want it written in the fraction form, and so this would be your final answer of 15/4. Now, we might want to go back and check this domain, so we'll do a real quick check on our domain. Typically, we don't have problems with this kind of equation, but we'll do a quick check. 4x minus 7 is greater than 0, so 4x must be greater than 7, and x must be greater than 7/4. Is 15/4 greater than 7/4? Yes, it is. So this is indeed my solution. Number 6, Another very nice, we have one logarithm on the left-hand side and no logarithms on the right-hand side. Usually if we have one side with no logarithms, that's what's telling us we're going to rewrite this to solve it. So again, you can also make a circle with this. So a little bit of just a pictorial representation. We can take 3 to the negative second power. So our exponential form would be 3 to the negative second is equal to, and then we go back across our equal sign, 2x minus 5. Or you can think of this as y, this is b, and this is x. Okay? So now 3 to the negative second power, we can rewrite that as 1 over 3 squared, or 1 over 9. I know you're seeing the fractions and thinking, don't like fractions. We got this. We're going to add 5 to both sides. So I'm going to put this step in here. So I'm going to add 5 to both sides. This is going to become 5 and 1/9 is equal to 2x. Now I am going to come over here to give us a little bit more room. 5 and 1/9, we're going to rewrite, because we don't like the mixed number form, we're going to write this as an improper fraction. 5 times 9 is 45, plus 1 gives me 46/9 is equal to 2x. We talked about a problem similar to this a couple of days ago. When we divide both sides by 2, that is the same thing as multiplying by 1/2. So over here on the right-hand side now, I get x. On the left-hand side, 2 will actually divide into 46 and gives me 23 over 9. And so this is my final answer. Checking that domain real quick if you want to do that. Sometimes that can help you eliminate bad answers. So this is going to be 2x must be greater than 5, and x must be greater than 5/2. And 23/9 is greater than 5/2. Right? So we're done. Excellent. Let's look at number 7. On number 7, I have 2 logarithms on the left and no logarithms on the right. So I will still be able to use this rewriting the equation in order to solve. I just have to condense the left-hand side. So we're just condensing the left side. So we condense this side by using the product rule. So I have log base 2 of x minus 2 times x plus 2. And this is going to be equal to 5. Let's check that domain real quick. X minus 2 must be greater than 5, so x must be greater than 2. If x plus 2 is greater than 0, x must be greater than negative 2. I think I said some 5s up here. I apologize. So our most restrictive domain is x is greater than 2. So we have to make sure all of our solutions are greater than 2. Let's rewrite this in our exponential form, keeping in mind our base to the 5th power. So 2 to the 5th power is equal to x minus 2 times x plus 2. Now I'm going to simplify the right-hand side. This actually multiplies together and gives me x squared minus 4. And the left-hand side simplifies to 32. To solve this, we add 4 to both sides, and I get 36 is equal to x squared. Now, since we know that x must be a positive value because it must be greater than 2, then we can just not worry about the negative, or if we take the square root of both sides, we get positive and negative 6. We reject that x is equal to negative 6 because it's not greater than 2. So the only solution we have is x equals positive 6. Excellent. Let's look at one more of these problems, maybe 2. We're going to take the left side again and condense because we do not have logarithms over here. On the right side, we will be able to rewrite this in its exponential form. To condense these logarithms, we rewrite this as log base 3 of 3x plus 1 over x minus 2. Now, again, keeping in mind those values for the domain, 3x plus 1 must be greater than 0. I know y'all are getting pretty good at this. So x must be greater than negative 1/3, and x minus 2 must be greater than 0. So x must be greater than 2. And once again, this is the most restrictive value that we have. So now, the next thing I'm going to do is I want to finish rewriting this. I kind of got stopped in the middle. Sorry about that. This is equal to the right-hand side of 2. Okay, so now we're going to rewrite this base to the power of 2. So I have 3 to the second power is equal to 3x plus 1 over x minus 2. 3 to the second power is 9. So 9 is equal to 3x plus 1 over x minus 2. Again, I'm going to cross multiply. So I have 9 times x minus 2 is equal 3x plus 1. Simplifying the left-hand side, I have 9x minus 18 is equal to 3x plus 1. Subtracting 3x from both sides, I get 6x on the left-hand side. Adding 18 to both sides, I get 19 on the right-hand side. And I divide both sides by 6. And I get x is equal to 19 over 6, which cannot be simplified. However, it is greater than 2. And so this is my only solution. Excellent. As I said in the beginning, we are only going to solve 1 or 2 application problems, but I did want you to see at least one example of the application because you'll see at least one on the homework, probably not on the quiz, and it won't be on the test, just in case you happen to really be listening to this section. So with that in mind, I'm going to look at this problem and I'm going to tell you for absolute certainty that this is not going to be on the homework or the test or the quiz. Not that kind of problem. I am going to work a couple of problems for you. That felt kind of good just to cross that off. I am going to work you a couple of example problems of these types of things. So number 2 is an excellent example. It says if $7,000 was invested at an interest rate of 4.6% and compounded continuously, how long would it take for the investment to become $8,798? And we want to round our answer to the nearest hundred. We will give you this formula, okay? So in this particular problem, I have 2 money amounts. The larger money amount is my final answer. So in terms of my equation over here. So this is my final amount, my A. 7,000 is my P. And my interest rate is going to be 4.6 divided by 100 because we have to have the decimal. So 0.046. And T is what we're trying to find. So how long tells me I'm trying to solve for T. So let's take this equation and plug in all of the pieces that we know. So we know that 8,798 is equal to 7,000 times e to the 0.046 t power, and that's where we'll start. The first thing we need to do is we need to get e to the 0.046 t power by itself. So that means we're going to divide both sides by 7,000. That is step number 1. So over here on the left-hand side, I have 8,798 divided by 7,000. Don't put that in your calculator just yet. Is equal to e to the 0.046 t power. Now, if you recall from the last video, the one that started section 5.4, in order to solve this kind of exponential equation, we have to take the natural log of both sides. So I'm going to be taking the natural log of the fraction, and we will put that in parentheses. In your calculator, you'll use all kinds of very nice parentheses in here. And this is going to be equal to, when we take the natural log of this e side, lovely things will happen. Don't forget the natural log and e cancel each other out. So what that then tells me is that on the right-hand side, I have 0.046t all by itself. And on the left-hand side, I am going to have this expression of the natural log of this quotient. Again, don't put this in your calculator just yet. Now we want to put that in the calculator, and then we will divide by 0.046. So to give you an idea of what we're going to get, we will take the natural log. Now, my suggestion to you is that you open your natural log, open that parentheses, type in that numerator divided by the denominator, and tell it to go to work. Now, if you do that correctly, I want to give you the little pieces steps. This should be 0.22861 with some other stuff. Go ahead and in your calculator, divide both sides by 0.046, leaving that in your calculator and dividing by that decimal. This is going to be 4.9698. It keeps going and going and going. It says round to the nearest hundredth. So time rounded to the nearest hundredths is 4.97 years. And that's how long it's going to take $7,000 to become $8,798. Excellent. This is a very similar problem, but it has two little pieces in it that I want you to see and pay close attention to. The first part is it's asking for the interest rate, so we are actually trying to solve for R in the problem. So what interest rate is needed for an investment to double if it is compounded continuously for 9 years? So we know what T is. What we don't know is we don't know A and we don't know P. But if my final amount is doubled, then what this tells me is that A is equal to 2 times P. So I'm going to show you how to start this problem, and then I'm going to show you the shortcut for any problems that have to do with doubling the amount. So to start this problem kind of the long way, we would put in place of A, we would put 2P is equal to P times E to the R, which we don't know what that is, times 9 power. Now I'm going to rewrite that also. If I divide both sides by P, this is going to give me 2 is equal to E to the 9R power. Now here's the shortcut. Every time you see a problem that asks you either to find the rate or the time when an amount has doubled, compounded continuously, you can set it up without the A and the P. You can set it up as 2 equals E to the RT power, and then plug in whichever one of those you have and solve for the other one. So in this case, we're solving for R. So to do that, we're going to take the natural log of both sides. So we have the natural log of 2 on the left-hand side and the natural log of E to the 9R on the right-hand side. On the right-hand side, those natural log and E cancel out, so I'm left with 9R. And on the left-hand side, I have the natural log of 2. Now, if I put the natural log of 2 into my calculator, I get 0.6931 and some other numbers. I'm going to divide both sides by 9, and that is going to give me that R is 0.0770 with some other decimals. But since R is actually my interest rate, it says remember to write your answer as a percent. So we go the other direction, we multiply by 100, so the interest rate is 7.7%. Don't forget to change that back to a percent. That ends section 5.4 and the very little bit that we're going to do in 5.5. I hope you have a great day. And we only have one section left. Bye.